Good afternoon and welcome to today's special interest group session with Bentley Systems for May 2020. This is a STAAD special interest group session, and today we're going to be focusing on STAAD.Pro, and in particular we're going to be focusing on modeling or generating finite elements. Let me begin this session by introducing myself. My name is Sabrina Tedeschi and I am a Senior Application Engineer here with Bentley Systems. I've been working for Bentley for 12 years and I conduct training courses and create training programs for all of the products within our RAM and STAAD product lines. Now, before working for Bentley Systems, I did work in the industry for an architectural engineering firm, designing large commercial structures out of a variety of materials, including steel and concrete. Now, before we begin, let's first discuss our STAAD special interest group sessions. We typically conduct our STAAD special interest group sessions in the United States on the third Thursday of each month at 1 p.m. Eastern Standard Time. If you're in a different time zone, this will be the same time as New York City time. This is the U.S. time zone. We do take 2 hiatus months throughout the year, so you should expect to see about 10 STAAD special interest group sessions in the United States. And if you go to the Bentley events page, you'll also see some international STAAD special interest group sessions are also available. Now, if you'd like to learn more about STAAD, you can go to the Bentley Learn server at learn.bentley.com, and you can register for new special interest group sessions or view past special interest group sessions by going to bentley.com and clicking on the events page. Now, we do supply you with a Bentley transcript after viewing this presentation or attending this presentation, and you'll be awarded 1 PDH credit. As a reminder, the SIGs are complimentary, and again, you can see the SIGs schedule from the Bentley events page, and it's also available if you go to upcoming events in Connect Advisor. So let's go ahead and discuss our agenda for today's session. Today we're going to be focusing on generating finite elements in STAAD.Pro. I'm going to start with a few basic tools that you may already be using in STAAD.Pro to create a finite element mesh. But the 2 main areas of focus that I want to spend the most of our time today on is using a parametric model to generate a finite element mesh in the STAAD.Pro Analytical Modeler. And I also want to show you how to generate a finite element mesh in the STAAD.Pro Physical Modeler using surface elements. Both of these 2 methods will provide you with the most control over your finite element mesh and will be more of an automatic process for you. So we'll move into those 2 topics today. We will now turn our attention to our first sample model that we'll be using today. This is a model that's already been started in the STAAD.Pro Analytical Modeler. As you can see from my screen, I am using STAAD.Pro CONNECT Edition for the duration of this special interest group session. Now, I'd like to start by mentioning what our goal is going to be for this overall session or for this building structure that we have here. My goal is to basically create a slab that goes over the entire system. I need this slab to be connected to the tops of all these columns as well as along each of these beam members that are kind of spanning column to column. Now, in any finite element analysis, displacements and stresses can only be determined at nodes or corners of elements. So it's basically impossible to accurately model the behavior of a plate using just a single element. So our goal today is to not just create that slab, but to create a mesh of elements so that we ensure that we are appropriately modeling the behavior, and we're going to be able to get the results that we want to. We're going to have proper connectivity with the supporting beams, and all of that happens at nodal locations. So since there is a need to evaluate displacements at arbitrary points within a slab around the perimeter, slabs will be modeled using a mesh of plate elements in such a way that the nodes of some elements coordinated with the points of interest within our slab area. Now, within STAAD.Pro, within the Analytical Modeler, we have a couple of basic tools that you can use that perhaps you're already using to create plates and also to generate a finite element mesh. And with this particular model, we're going to start with those workflows, and then we're going to move on to some of the more advanced workflows that we do have available now. The first thing to note is that all plate elements within STAAD.Pro consist of either 3 or 4 noded elements. To create one plate at a time, we're going to go to the Geometry tab in the ribbon toolbar, and we're going to locate our Add Plate tool. Now, the typical basic Add Plate tool will add a 4-noded plate, or if we use the pull-down menu, we can also create a triangular plate element. Now, what I'm going to do first is I'm just going to start with this Add Plate tool. You're going to notice your cursor is going to change, and then you're just going to select 4 nodes. You do want to select these nodes in consecutive order around the perimeter. It doesn't really matter if you go clockwise or counterclockwise, but they do have to be in order along the perimeter in one direction or the other to ensure that you don't start creating some warped plates. Now, whenever you activate one of the modeling tools within STAAD.Pro, what you're going to notice is in the bottom left-hand corner of your screen, the status bar will give you some instructions as to what the program is expecting next. This is especially useful if you are using that tool perhaps for the first time. Now, once you're done creating that plate element, of course, your cursor is still active, so you can keep creating more elements if you need. If you want to deactivate that tool, you're just going to reselect the Add Quad Plate tool again, and then our plate element has been created. Now, to select any entities within STAAD.Pro, we're going to go to our Select tab in our ribbon toolbar, and we're going to go to our Plates cursor for this exercise, and we'll be able to select our plate element. Now, as I mentioned earlier, we're never going to typically just create one single element in a particular bay. I mean, if I take a look at this slab element, we'll call it for now, it is actually only connected to the top of the columns. Currently, there's no connectivity with the supporting beams, which should also be sharing stiffness with that slab element. It should also be sharing loads with that slab element. So for those reasons and for others, we're going to create a mesh from this element. Now, this method that I'm showing you right now, this I would call my super element method. It means I'm going to create an overall plate, and then I'm going to chop it up into smaller finite elements. Now, what you probably noticed is that when you activate one of those cursors and select an element on your screen, an additional tab will become available in your ribbon toolbar to provide you access to the tools that would be most helpful for whatever you have selected. If you have more than one entity type, you will see additional tabs available up in the ribbon toolbar. Now, most of the tools that you're going to see on these like element-specific ribbon tabs are also available in other areas of the program, but I definitely like coming here because I think it's easy to find the tools that I'm most interested for or in based on what I currently have selected. So I've selected a plate element, and now I want to chop it up into smaller pieces. So with that element selected, I'm now going to select the Plate Mesh tool. Now, when creating a finite element mesh, you're going to have an option for polygonal mesh or quadrilateral meshing. Quadrilateral meshing will just create typical 4-sided elements. It will be a very regular geometry, but it also does not allow you the opportunity to add anything unique within your floor system, such as if you have any like floor penetrations or openings within your slab. The quadrilateral meshing probably isn't the right choice for you. In this case, quadrilateral meshing will work, so I'll go ahead and select that. In a future exercise, I'm going to go with polygonal meshing, so we'll be able to see the difference between what the quadrilateral and the polygonal meshing will do for you. So let's go ahead and click OK, and then we're going to be ask some questions. First of all, we do have the choice to create a triangular element if we want. It's defaulting here to quadrilateral, and I'm going to keep the quadrilateral option selected. Now, as a reminder, it's gone ahead and given me the length of each side within my overall shape. This is going to be helpful information because as you generate a finite element mesh, what you're especially interested in is to try to get your element sizes as close to either a square or an equilateral triangle as possible, which means you're going to want to create your number of divisions. That's what the DIVN field is. So your number of divisions along each side. You're going to want to create it so that it's fairly uniform. Now, for my particular model, it's almost square, not quite square, but I'm still going to say 10 divisions along each side is going to work for me. I'm going to click Apply, and then you can see that my finite element mesh has been generated. What we're also going to notice is that automatically, let me zoom in a little bit here, is that automatically STAAD.Pro broke the supporting beams or segmented them at the same points where that finite element mesh was intersecting the member. So the default position for STAAD.Pro is if that a node is added along a member, it will segment that member. Now this is significant because we do want to ensure proper force transfer, proper stiffness in our full finite element analysis. So this is the exact situation I was looking for this particular model or situation that I'm trying to simulate in STAAD.Pro. Now, in addition to that method, that's a super element method, you're going to create an overall large plate and then break it up into small ones. I do have an option to skip that first step and go straight to a finite element mesh. To do that, you're going to access your Generate Mesh tool. So let's go ahead and click on that tool. Again, my cursor is going to change. Again, my status bar is going to give me some detailed information about what's expected next. And then I'm going to create a finite element mesh, and I'm going to go ahead and pick this bay this time. Now, one of the unique aspects of this particular tool is it's not going to limit your overall slab area to just a 3-sided or 4-sided figure because it knows you're going directly to a finite element mesh. So if I had, a non-regular shape or geometry, it would allow me to select additional nodes. Again, you want to watch for things in the same plane. You don't want to produce warped plates. When you're finished, you could either right-click or just click back at your starting node. It'll register that the geometry is complete. And then again, we have the same option we had before. The quadrilateral meshing will bring us to the same exact dialog that this one had, or we can go with polygonal meshing. Now again, polygonal meshing gives you a few additional options, and one of the main options is you can add an opening or floor penetration in at the time that you're generating your finite element mesh, which may be very useful for you. So this time I'm going to say, yes, I do have an opening in this area, so I'm going to go with polygonal mesh. Now, polygonal meshing will automatically bring you to a triangular meshing system instead of a quadrilateral. So I've chosen this, so this is where I've decided. Now again, this is about a similar size that my other area was in, so I'm going to go again with 10 divisions along each side, okay? If I want to create a hole within my slab, I can go to the holes area. I'm going to click on the Add New Hole icon, and then I have a few different options here. I can create a polygonal opening, a circular opening, or an ellipse. I'm going to create a polygonal opening, and I'm going to add a few additional rows to enter the full geometry that I'm going to have. I'm going to start with my starting node. Here I'm going to enter 13, 15, and 22. So what is important to note is that these are using global axis coordinates, so you will have to know or think about this a little bit before you get to this step of where you are in space, okay? So I'm going to enter my first node, and then I can add additional rows as needed for the rest of my geometry. What you're going to notice is I do have some lines starting over in this area. That kind of gives me a good idea where I am in space. And then finally, you're going to go back to your starting node. Okay. I know this is my overall slab area, and since this rectangular opening that I'm seeing here is appearing in my graphic, I do know that it is in the right location, or at least within the slab area. If I had picked coordinates that were maybe like out here somewhere, I'd be able to see that reflected in this image. So that gives me a good second chance to make sure that I got my coordinates at least within my slab area. So once we're done, we're going to go ahead and click OK. Our mesh is going to be generated, and let's go ahead and select those plates. Maybe that way we can see them a little bit more. So you can see that here are my plates it created triangular elements, and it created an opening. Now, one of the things you might have noticed is that I am focusing on one bay at a time. And so for both of the methods that I've shown you so far, the super element method using the add plate tool or the generate mesh tool, you would have to focus on one area at a time. The reason for that is because I want it to connect to these interior members and to the tops of these interior columns. And using these two tools, the only way to do that is to focus on one bay at a time. In addition to that, if my overall goal is to create a slab over this entire area, I'm also going to want to pay special attention to the number of divisions I have along each side as I create additional or adjacent bays, because again, I want the plates in this bay to coordinate with the nodal locations in the adjacent bay. So a little bit of extra planning will be needed. Now, this may be, if you have a very large area, slightly time consuming. So that's why I want to focus the rest of this session on two additional tools which are going to allow you a little bit of further control and also an automatic connectivity to those interior elements. So you just kind of have to create an overall slab area. Now, if working in the analytical modeler is the workflow that you prefer, then I'm going to lead you to parametric models. And if you are starting to use the physical modeling workflow, then we'll go ahead and see how you can control your finite element mesh using your surface items. Now that we've gone over some of the basic finite element mesh generation tools that we have available in STAAD.Pro CONNECT Edition, let's also take a look at a more advanced procedure, which is to create a parametric model to represent your finite element mesh. To navigate to this area, you're going to go to the Geometry tab in your ribbon toolbar, and then you're going to select the Parametric Models option within the Plate Tools. Now, STAAD.Pro allows you to model surfaces by automatically generating a mesh from a set of parameters. You can preview the final mesh state of the wall, slab, or panel before deploying the mesh entity into the remainder of the model. This way, you will be able to visually examine several trials or prototypes to find the most alternative solution. So here what we're going to do is we're going to get started by creating a parametric model, which again is just a prototype model of a finite element mesh. It's not officially committed to the STAAD.Pro input file until you tell the program that you want to accept the mesh and send it over to the main application. So over in the Parametric Models dialog, I'm now going to click on the Add button, and then you're going to notice your cursor is going to change. So what I'm going to do is I'm going to click along the perimeter, the entire slab area. I'm going to start at this first node. Again, my status bar at the bottom left-hand corner of the screen will give me some hints about what the program's going to be expecting next from me as far as workflow goes. Now, once you finish, you can right-click to close a polygon or just click right back at your starting node. Now, each model within STAAD.Pro contain a couple of different parametric models, even for the same area. Again, these are prototypes, so what it'll do is it'll allow you to, if you wanted to create a couple, so you can kind of preview what the changes would look like, that is allowed. So for that reason, you can name yours. I'm just going to create one parametric model for my system, so I'm just going to call it Mesh Surface 1. For my system, it will be a slab. And I'm going to select a meshing type. Now, typically, I usually keep all of these set to their defaults, and then I'll play around with the parameters once I get my preliminary mesh set up. The important thing that I want you to point your attention to, however, is this Create Density Objects from Internal Nodes or Beams checkbox. As you probably noticed, I just clicked along the entire envelope of where my slab is going to be. I didn't select any interior beams or interior nodes in those situations. Now, by creating a parametric model, STAAD.Pro will be able to automatically pick up when there is a beam or a top of column that's intersecting where that slab or system, depending upon what you're creating, is going to go, and it's going to automatically connect the finite element mesh to them. Now this is going to save me a little bit of time because then I won't have to focus on just one bay at a time and make sure that my different bays are kind of coordinated together as far as like nodal locations or number of divisions along each side. So I'm going to go ahead and click OK here. And as you can see, the program has set up a mesh for me. Now, one of the things that are advantages that you have for using parametric models is your ability to change some of the meshing parameters after seeing your preliminary mesh. As you probably noticed with the Add Plate tool or the Generate Mesh tool in the main application, I enter the number of divisions, it generates the mesh, but there's really no opportunity to change the mesh density after I create it. So your workflow in those scenarios would be to delete it and then add it back in with a different density if you wanted to investigate something else. Here with a parametric model, what I can do is I could just change some of the meshing parameters. So here I'm going to change from standard mesh to a basic mesh. I'm going to click apply. It's looking a little tight. I'm going to change the target element size. I'm going to click apply again, and then things are starting to look a little bit closer to the mesh I would normally want to create. And then again, you're going to notice that there are no elements that are going over, across, or spanning across a beam member. They're connected to all these interior beams and interior columns. When I send this over to STAAD.Pro, STAAD.Pro will automatically segment those supporting members so that they are coordinated with your finite element mesh. They're sharing stiffness, they're sharing loads, and so forth. Now, another advantage that you have of using a parametric model is that you're able to control the mesh even more than what we have here. So let's go ahead and take a look at our parametric model window. So I'm going to go ahead and scroll on down. So here's my mesh surface, and it identifies its boundary. And then I can see I have a bunch of other types of objects that I can create. I can create a density point or a density line. This basically means I want to control where the finite element mesh is in addition to just attaching to the interior columns and beams. If I wanted a density point, say for example, I want to put a point load and I want to coordinate it with a nodal location, I can tell the program where I want nodes to be, and it will go ahead and incorporate that into my mesh design. I can create regions, and I can also create openings. So let's take a look and create a couple of these different types of objects. Let's start with openings. So I'm going to click on openings as the option, and then click on the add button. I have the option to create a polygonal opening or a circular opening. So I'll start with a polygonal opening and then click OK. Now I find it easiest to set up a mesh to give me basically points or snap points within my slab area. So I've already created a mesh at this level. I'm assuming that wherever this mesh is, I've coordinated that with where the other items are going to need to be within this slab. I did use a regular mesh, but of course you can create an irregular mesh as well. So using this option, let me zoom in here a little bit. I can just create a polygonal opening. Let me create one right here. And then again, just click back at your starting point. And again, I'm just using those grids as snap points. And then we can see the opening has been created. I can control the number of divisions along each side, and I could even change its coordinates if I needed to. If I wanted to create a circular opening, again, I could just click on openings, click add. This time I'm going to say a circular opening. I'm going to use my grid again. This time what the program is wanting me to do is pick a center point and then identify its radius. I can enter the number of divisions along the circumference. I'll keep that at 10, and then we'll click OK, and then you can see I have a circular opening available there. Now again, I can change this radius after I create it. So I guess where I clicked was 5 feet. Let me change this to 3 feet. Click apply, and then you can see you can change the number of divisions, you can change the radius fairly easily. Now let's move on to the regions area. So what a region will do is it'll kind of identify an area within the slab where you, again, want to break your finite element mesh. This might be significant if eventually you're going to add a plate pressure load and you don't want to do it as a partial load. You kind of want to define a region for where that load is going to exist. So that might make some modeling steps later on a little easier. Also, if there's any place within your slab that would have a change of properties, like a change of thickness or anything like that. You may need a region or like to control a finite element mesh within your overall slab or overall field of finite elements. So here again, I'm going to create a region. You just highlight the item you want to create, click Add. I'm going to enter a region type. I'm going to go with a polygonal region. Again, I'm going to just coordinate with here, and I'm going to enter a region. Again, I'm going to click back at my starting point. Let's zoom in to see what that looked like. So now we can see that it basically created an area where my finite elements aren't like going over past this region boundary. They're kind of respecting that boundary. They're kind of breaking themselves along that point. So again, if I had loading eventually that I wanted to add here, or a different thickness or anything, any other reason, that might make it a little easier for me. And again, you don't have this kind of tool with the other traditional like add mesh tools, which is what makes this significant. Now that's a region, so that's a polygonal region. Very similar to that, again, just controlling where your points are. I can create a density point. Let's go ahead and click the add button. So let's go back to my grid. So again, if I have like any point within the slab where I want that to be an official node location, I can do that. And if I wanted a density line, that would be like a line somewhere where, again, I'm just going to break your finite elements across. Go here, click Add, and then you can break your finite element points, say, right across here. So let's talk about the advantages that you get for using a parametric model. And this is kind of a more advanced meshing technique if you're using the analytical modeler. So the first advantage would be prototypes. It will enable you to preview the final mesh state of a wall or slab or panel before deploying the meshed entity into the remainder of the model. Several trials or prototypes can be visually examined before committing it to the most suitable one. And this will greatly minimize the inconvenience of ending up with an undesirable meshed panel. Your second major advantage is recognizing interior nodes. So during the process of meshing, the program will automatically take into consideration existing nodes that lie within the boundary of the panel but are not chosen as corner nodes of the panel. You can simply define the panel boundary like we did here. So the remainder of the nodes will be automatically considered by the program as control points, which is to say that elements will be created in such a manner that some of those elements will have these nodes in their incidence list. Control points might be panel points of a truss which supports a multi-span slab, or a foundation slab that supports several columns. And finally, your last advantage is to be able to control your finite element mesh with either density lines, density points, and regions. So it allows for the definition of lines, points, and regions on the surface, and control where nodes will be located within your finite element mesh. Again, after creating your finite element mesh in a prototype model, you can adjust the bench density and preview all that information before committing it to the full system. Now, for this particular model, I've kind of focused on just like a concrete slab over a floor system. I do want to make sure the point is made that there are a lot of other applications. It doesn't have to just be used for slab. It doesn't have to just be used for concrete. So you can use parametric models to create a wall system, any type of panel, steel plates, anything where you're going to normally create some type of plate element. Parametric models can be used for that. The final thing I want to mention is in STAAD.Pro CONNECT Edition, version 22, update 3, we have added the ability to import a finite element mesh into the STAAD RCDC for the design of concrete walls if that finite element mesh was created as a parametric model. So again, you're going to want to check the version of STAAD.Pro you're using. You're going to want to at least update 3 to make sure you have that capabilities. And of course, that's probably your best workflow for designing concrete walls that were modeled in STAAD.Pro, is to kind of create them as a finite element mesh, analyze them with that meshing system, and then transfer them over to the STAAD RCDC workflow. Now at this point, I've previewed and massaged my mesh the way I want it to, and I'm ready to commit it to my STAAD.Pro model. Again, I could have created more than one prototype if I wanted to, but I like this one the way it is. Once I'm ready to make that official move over, I'm going to click on this item. So we're going to make sure that if you have more than one system in here, you're going to want to select the one that you created that you like. And we're going to go ahead and say Merge Mesh. What that's going to do is it's going to officially create these plates in the input file. So now if I go to the plate layout area, I could see that the plates have now been created. They're officially committed to the input file. And as far as this point moving forward, my workflow picks up the way it normally would in STAAD.Pro, where I'd assign properties, loads, analysis, and design commands. I don't return to the parametric model area. All my meshing is complete at this point. And of course, if we take a closer look at this model, we can see that our openings are represented. We'll be able to see the node points. Here's my density line over here. And of course, I have my region here. So this did allow me quite a bit of control over the finite element mesh. And of course, I could have continued on as much as I want to get this exactly the way I want it. For the last workflow that we're going to show today is to use a physical model workflow to generate your finite element mesh. And to accomplish that, we're going to use surface elements. It's basically the physical modeler's version of a plate. Now, this model I have on the screen is basically identical to the analytical model that we used in the previous exercise, except it was created with a STAAD.Pro physical modeler. So far, it just contains beams, columns, and supports. So what I'm going to do is I'm going to go back to the physical modeler. And to do that, I could just click on the workflow panel. This will bring me to the STAAD.Pro physical modeler. Now, in case you're a little bit newer to the physical modeling workflow, let's go ahead and talk about it very quickly. So the physical modeling workflow is used to model your structure in the STAAD.Pro physical modeler using physical members. The physical model is used to draw structural elements as they are physically constructed. So let's visualize, like, say, a beam to girder scenario. Typically in the STAAD.Pro Analytical Modeler, if you have a girder that's supporting some infill beams, what you would do is you would segment that girder member so that basically it shares common nodes with those beam members. That ensures proper force transfer through the analysis process. Now, with the physical modeling workflow, that wouldn't be necessary. You can basically construct that girder as it would exist in the field, possibly, like, say, from column to column. Span that infill beam right to that girder without the need to segment that girder at all. Now, if you're using a physical modeling workflow, it's important to note that analysis and design in STAAD.Pro still exists in the analytical modeler. So basically what you're going to do is you're going to use the physical modeler as basically a modeling tool to create your structural geometry, and then you're going to send that data over to the STAAD.Pro Analytical Modeler, and basically what it's going to do is it's going to build your input file from the information you put into the physical modeler. The physical modeler is going to include such things as all of your structural entities, so plates, beams, nodes, columns. All of that information is going to be created here. It would also contain all of your properties, your supports, and your loading information, load combinations, load cases, and so forth. Once you get over to the analytical modeler, you're still going to use the analytical modeler to define your analysis commands and define your design information, your design commands through that workflow. So now, as I mentioned earlier, we can use the STAAD.Pro Physical Modeler to basically create a surface entity that's going to translate into a plate system once we get over to the analytical modeler. So whenever we're in the Modeling tab of the ribbon toolbar, within the physical modeler, we're going to see all the different items that we can create, and I'm going to create a new surface. Just like the parametric modeling workflow, it's not necessary to do one bay at a time. You can do your entire surface over your entire floor, and the program, when it creates that analytical model, it will recognize your interior beams and your interior columns as basically density points and assign the proper connectivity through nodes. So what I'm going to do is I'm just going to click around the perimeter. Again, I just go in order around the perimeter. This will ensure that you don't have any warped plates if you go around the perimeter. It doesn't matter if you go clockwise or counterclockwise. When you're finished, you're just going to double click on your first node, and then we're going to be able to see our overall surface has been created. If you want to review any information for this surface, you can go to the Spreadsheet tab of the ribbon toolbar, and you can navigate to the appropriate area. Here I can just go to the surface area. My model just contains one surface. Now, whenever you create a surface entity within your physical modeler, again, it's going to automatically mesh it when you go over to the analytical model or when you basically build the input file. So within the physical modeler, you can control the mesh density that will be used when the analytical model is created. To control that information, you're going to go to the Data tab in your ribbon toolbar, and you're going to find this icon for Options. Let's go ahead and click on that. So once I get to the Options dialog, I'm going to go ahead and click on the Analysis Model tab, and I can see that I have a lot of control over how the analytical model is going to be created. Let's take a specific look at some of the surface tools that are available. The first thing I'm going to do is see that the option to segment surfaces is checked. This is what's going to tell the program that I want to create a finite element mesh and not just create a plate over the entire area. Next, I'm going to see the mesh type that will be available. I can select quadrilateral or triangular plates, and I can enter a maximum allowed distance between nodes. I'm going to set mine at a 6-foot density. Let's go ahead and click OK. Now, before I leave the physical modeler, I am able to preview what the analytical model is going to look like. So what I'm going to do is I'm going to go to the View tab in the ribbon toolbar, and I can click on the Analysis Model. So that's what it's going to look like so far if I was to create the analytical model right now. Let's go ahead and build our analytical model. And what I want to show you is that you can go back and forth and change your mesh density. And that's going to be a very powerful tool because this really is the only area in the program where you can change mesh density for a finite element mesh after it is officially created in the input file. So what I'm going to do is I'm going to go up to my quick access toolbar and I'm going to say to return to the analytical modeling mode. Now during this process, the physical modeler is basically transferring its data over to the analytical modeler. It's building that input file and committing the information over to the analytical modeling workflow. I do have some warnings indicated in the Output tab at the bottom of the screen. This is basically letting me know that my physical model isn't really quite complete. I have some elements in here that maybe weren't assigned a property. I don't have loads. I don't have thicknesses of materials or material properties assigned. And I'm okay with that so far because I'm not really done with my modeling workflow. I just kind of want to see what it's going to look like. So I'm going to go ahead and click OK. And I'm going to confirm that I want to close the physical modeler. Again, right now my analytical model is being created and I can take a look at the system as it stands right now. I can confirm very easily that, again, this finite element mesh is coordinated with my interior beams. The interior beams were segmented. It is attached to the column. This is exactly how I would want a finite element mesh to look. But I'm not quite done with my modeling process. Perhaps I've come here and decided that I need to add some complexity to the system or perhaps change my mesh density. So let's return to the physical modeling workflow. Again, I'm going to go to the Data tab in the ribbon toolbar, and I'm going to go back to this Options area. Perhaps I want to investigate a tighter mesh, so maybe I'll go down to 3 feet for my mesh density. What's also nice about the way the physical modeler works is that you can change your units basically on the fly. You can change your units globally by selecting this option within this dialog, or if, say, for perhaps I wanted to enter 36 inches, you could just put the typical nomenclature for inches, type it in, and it'll convert it automatically for you. So let's go ahead and just click OK. I'm going to save my model in the physical modeler, and then again, let's return back to the analytical modeling workflow. So each time you come back to the analytical modeler, basically what the program does is it recreates your input file with the data that currently exists in the physical modeler. So here we can see it rebuilt that system. It was able to change my mesh density, basically on the fly. Now, what happens if you have a model that contains more than one surface? So maybe perhaps you have some walls, maybe you have a few different slabs, pieces of information like that. Well, you can change the density on a per element basis. So what I'm going to do is I'm going to go to the surfaces area. I'm going to select properties this time. And let's scroll on over in this spreadsheet. And here you can see that if I had more than one surface, I can, instead of using the global criteria for the analysis options, I can control the mesh size per each surface element. So say for this surface element, I want to go with 5 feet instead. Now that my global criteria is set at 3 feet, I've changed it to be 5 feet now for this particular element. So if I had other surfaces, if I didn't override the mesh size, it would use the global criteria. But this one I've said I want to use this specifically. Again, let's go back to the analytical modeler, and we can see that we control this on a surface by surface basis. And so here you can see that I've controlled my mesh density on this surface specifically. Let's return to the physical modeler now, and now I'm going to add a little bit of complexity to this system. So just like we saw for parametric models, I can add regions, I can add density lines, and I can add openings. Now you're not going to see an option to add basically a density point like we had seen in the parametric models, but basically if you want a specific point within your surface area to be considered a node, all you have to do is basically create a node within that level, and that's the same exact thing as creating a density point. So if you want, for whatever reason, a specific point to be considered and to attach your finite element mesh, you're just going to create a node within that area, which you can do through the node spreadsheet in the data area. So let's go ahead and talk about, while we're here, let's talk about versions of STAAD.Pro. So in order to have the STAAD.Pro physical modeler, you do need to have at least STAAD.Pro CONNECT Edition, at least the base release. So the physical modeler is something that was introduced with STAAD.Pro CONNECT Edition. Along with the physical modeler in that version, we also updated the graphical user interface. We have better connectivity with things like ISM and also the RCDC, as well as a few other options that are available. But in addition to STAAD.Pro CONNECT Edition, we have a couple of updates that I want to make sure everybody's aware of as you move forward if this is the workflow that you're going with. The first is STAAD.Pro CONNECT Edition version 22 Update 2. In that release, we included the option to add polygonal and circular openings within a surface system within the STAAD.Pro physical modeler. So if that's geometry you're interested in, you're going to want to make sure you have at least Update 2. And then in addition to that, we released STAAD.Pro CONNECT Edition version 22 Update 3. In that release, we have provided the ability to create surface regions and region loads, and also reference lines and reference line loads were added in that version. So I'm going to show you how to kind of add all those different entities, but again, to get all that full functionality, you're going to really want to make sure you have the latest and greatest version of STAAD.Pro CONNECT Edition, because again, some enhancements were added that you might be interested in. So let's go ahead and get started by adding our openings within our area. So as I mentioned earlier, in order to create any type of entity, you're going to go to the Modeling tab in the ribbon toolbar in the STAAD.Pro Physical Modeler. Now, just like for parametric models, I find it easiest to create a grid at that particular level to give yourself some snap points. So I've already created a grid for this system. So I'm just going to go to the View tab in the ribbon toolbar and basically turn on my grid. I created a regular grid. You do have the option to create an irregular grid in the physical modeler. So here, let's go ahead and just start with creating a polygonal opening. So you can see here, I have all my snap points available. Just click back, double click actually back to your starting point. You can create a polygonal opening. and you can create a circular opening. Now here you're going to predefine your radius. I'm going to say 3 feet, a number of facets along the perimeter, and then we'll go ahead and click OK, and then I can click on any snap point I have in the model. If I want to make any changes to any of those options, let's see, let's go to the Spreadsheet tab of the ribbon toolbar. I can go to my Openings area, and I can also go to my Circular Openings area. Here you can see very easily I can change my radius to 5 feet, which allows me to kind of make changes as I go along. That's a very desirable or a very big advantage of creating your physical modeler is the ability to make changes, because of course as you work your way through the life cycle of your project, there may be changes that are made and you may not know at the beginning of your modeling steps, say, where all the openings and regions within a floor slab are going to need to be located. So this will allow you some flexibility there. So we went ahead and created some openings within the system. Let's also go ahead and take a look at the region. So here you can see I can create a region. Same idea as we saw within the parametric model. Is basically a region basically defines an area where you're going to control even further your finite element mesh. Sometimes this might be if you have a significant load over a particular region, if you want to change the properties, or you can even, with a physical modeler, adjust the mesh density for a region independent of the rest of the slab. Now, a region must be contained in an overall surface area. Okay, so when you create a region, it's basically assigned to a particular surface. So if I create it within the plane, within the boundaries of surface 1, which is the surface I'm working with, then it's going to be, this region is officially going to be assigned to surface 1. So here I can basically create a region within my area. So here I have a region here that is defined. Let's go ahead and take a look at that, where that is in the spreadsheet area. So here I can go to the region. So automatically, since it's within the envelope of surface 1, it's automatically going to assign it to surface 1. So I don't have to do any work there. Now, if perchance you had two different regions that were overlapping each other, the region with the higher priority would govern. So that's what basically the priority field does. Now, if your overall surface was using the global analysis criteria, you do have the option to adjust the mesh size for the region independent of the rest of the slab. I have done a trial with this. It looks like if you do a customized region for the overall slab, then it's going to use that for the region as well. So this mesh size would be basically if your overall surface was using the default criteria, then you can control it further for just this particular region. Now, in addition to that, let's return to the modeling area. And we also have a new option to create a reference line. So a reference line would basically be used to control the mesh of a linear portion of a surface. And you can also use it to apply, like, say, a line load to a surface area. Nodes will be created to define the reference line, and you can add a line load to reference lines, which is significant. So let's go ahead and say I want to add a reference line, and let's say I'm going to add one along here. I'm going to right click to I'm just going to deselect that tool to kind of basically turn it off. Again, I can go to the Spreadsheet tab in the ribbon toolbar and then go to the reference line area. And again, I can control the mesh size of that along that reference line. Okay, so let's talk about some of the extra unique things that we have available to us with things like regions and reference lines that basically the physical modeler is going to provide for you or allow you to do. That's maybe a slight advantage over some of the other things or some additional benefits that you would have for using this system. Now, one of the things is that when you use a physical modeling workflow, you assign all of your properties and loads in your physical modeler. For that reason, it might be slightly easier if you do have some of these unique geometries to create that physical model, because as you can see, I can assign a thickness to a region versus the rest of the slab. I can assign a pressure directly to that region. I can do the same thing for a reference line. So here you could see I can add a line load across here. That might actually be an easier way to get that type of information in. As we saw with the parametric models, I was able to create those regions, but I don't assign properties to the finite element mesh until I officially commit that finite element mesh to my STAAD.Pro Analytical modeler, and then I'd have to kind of hunt out which finite elements I want to assign a certain thickness to versus the rest of the area, or say a certain load or pressure assigned to them. So this might make that a little bit easier if you do have some unique geometries. And also, again, if you want a particular density point, maybe you're adding a point load somewhere within this system, for example, you could just add a node within the area and it will go ahead and detail it accordingly to make sure that that node corresponds with the finite element mesh that's eventually going to happen. So let's go ahead, and again, before I build my analytical model, I do like to see what the analysis model so far is going to look like. So here I can see all of those pieces of information. Let me go back to my spreadsheet area and my surface properties. I'm going to go ahead and just, actually, I am viewing my analysis model right now. I want to make changes not in the analysis model. I'm going to tighten this up to go with 3 feet. Again, I can view to see what that's going to look like. That looks a little bit better to me. Again, I can define my properties for that region or assign loads while I'm here. So far, I'm not at that point in my workflow, so I'm just going to save this model, and I'm going to return to my analytical modeling workflow. Now, when you use a STAAD.Pro physical modeler, what the program will do is when you create your analytical model, it will lock up your input file as far as entities within your model, properties, supports, and loading. So all those portions of the workflow, since they're done in the physical modeler, they are not items that you can change or add to once you get to the analytical modeler. So let's go ahead and take a look at what that looks like when you get over to STAAD.Pro. So let's go ahead and take a look at our command file. Again, my model is not completely finished yet, but what we're going to see is that when you create an analytical model, it's going to give you a block of data that says start, do not edit, and things are grayed out here. So we can't really make any changes for this particular model. But again, it did build all this for us. And it's going to finish with a block of data saying do not edit. Everything within that block of data is going to include all of your geometry, all of your properties, all of your materials, specifications, supports, and loading. Those are all items you're going to do in the STAAD.Pro physical modeler if this is the workflow that you go with. Once you get over and build your analysis model and you get completely done with that portion of the workflow, you can go ahead and add in your analysis commands and proceed in with the design of your structure, adding in design commands depending upon what type of system you are investigating. Now, if there comes a point where you want to drop that physical model, say you've made all the modeling changes you want, you don't feel it necessary to retain your physical model, we do have an option to drop your physical model if you prefer to go with a fully editable analytical model. So if we go to the Utility tab in the ribbon toolbar, you can tell the program you want to drop your physical model, and that will basically break the connection between the two. This is a one-time command that you can issue for your project. So once you drop your physical model, you can't really say, I want to go back to a physical modeling workflow again. It'll break that link and you can only do that one time. For that reason, you may want to consider doing like a save as if you kind of feel like you want to retain that physical model and at least a model that has a link with it. But if I drop the physical model, then everything would become active and I can edit the model directly within the STAAD.Pro analytical modeling workflow if that's an option I choose. So hopefully over the course of this special interest group session, you got a lot of information about generating a finite element mesh, or basically the tools we have available in STAAD.Pro. We have some basic tools that might be great for some basic geometry areas. If you have some more advanced geometry, or if you want a little bit more control over the meshing of a finite element mesh, then I would definitely recommend, if you're using an analytical modeling workflow, to consider generating your finite element mesh using parametric models. If you're using a STAAD.Pro physical modeling workflow, then I definitely recommend the surface entities. Both of those would be great options if you have some unique geometry that you want to enter for your finite element mesh, and if you want basically ultimate control over the finite element mesh. Now, one last note that I want to add is that both the physical modeler and the parametric models, well, basically, surface elements from the physical model will automatically create a parametric system in your STAAD.Pro main application. So for that reason, again, both of those workflows would be compatible with RCDC as far as concrete wall design. I used a surface element here, like a slab, I'll call it. But both of those would allow you the workflow to then work with STAAD RCDC if you were designing walls. Those would have to be, of course, vertical elements, and then STAAD RCDC might have some limitations on geometry and so forth, but at least it would allow you to get your finite element mesh over to that program for the purposes of concrete wall design. So again, hopefully you've gotten a lot out of this and you've learned some new tools or found a tool that works best for whatever it is that you're working on as far as a finite element mesh goes in STAAD.Pro. So I want to thank everybody for attending this session. And again, for the full physical modeling workflow, I definitely upgrade to the latest edition of STAAD.Pro CONNECT Edition.